podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to relate two physics concepts that we often think outside of physics, and those would be work and power. So, work, from a physics point of view, is how, let's see,
we gave the formula. I think the formula is a good definition. It's force over a distance.
Yeah, so applying a force over some distance.
Right.
Work leads to energy changes.
Right.
So if you were to lift an object over your head, that would require work because you gave the object gravitational energy.
Potential energy. Right.
Yeah. Power is how fast did the work get done?
So does it really work over time?
Right. So the equation for power is work divided by time. So I think a lot of people get the concept of power confused, just like they get the concept of work confused. So if we walk around with an object all day, we haven't done any work because it hasn't changed its position. It hasn't acquired some long-term velocity. So the work that is done is zero, which means it took no power either. So that's a misconception I think a lot of people have. If we want to look at this from a more practical standpoint, we could talk about strength versus power. And so as a coach, I'm concerned about how strong my athletes are versus how fast they are. Now, both are important. But I'm going to be honest, in the sport of water polo, and even if I coached some other sport like wrestling or football or basketball, there's not too many opportunities to squat something really heavy and show that off in a game. That doesn't happen too often. I am concerned about how quickly and efficiently we can perform a movement, though. So when we start talking about power in this building, we talk about APT, athletic performance training. And Coach Bundy and the PE teachers do a fantastic job of teaching your muscles to be powerful. So how fast can you perform X, whatever it is?
So maybe swim the length of the pool or something like that.
Right. So how does that translate? So, in my sport, how fast can you pick up the ball and throw it accurately? How fast can you swim to the other end of the pool with your head up? How fast can you swim to the other end of the pool with your head down in the water? And so we now in this place, we teach our athletes how to do this through a variety of exercises and yoga movements and lifts that work here. The bench, so strength, traditionally we would think of like a bench press or a deadlift or a squat. And so this is more old school athletic training. And it's not that these items aren't important, but really it's how fast can you bench press this weight in 20 seconds, or how many times can you bench, how many times can you deadlift this in 10 seconds, and so on. So that's what a coach is more concerned about, power. If you're going for the world's strongest man, you're actually still more concerned about power because you have to pull a bus, or you have to throw empty kegs over a high bar, yeah, or whatever. So it's not about doing it once, it's about doing it repeatedly to get you stronger. We used to do this old power lab in physics where we would run stairs. And right now they've got a huge sigh of relief that we didn't make them run stairs. So what we would demonstrate is, okay, you would walk up these stairs, and we would time it. So we would walk 1 foot, every foot hits every step, and then we would walk it again, where you would go every other, so right, then left, then right, then left, etc. Then you would run, where every foot hits every step. Then you would run again, where right, then left, then right, then left, and then you would, I would call it bound. And we would time it. So one of the first questions would be, okay, look, which situation does the most work, or is the most work involved?
Work is force over distance, so the work must be the same in all the cases.
It was, yeah. The work was exactly the same because we have increased the GPE
The same.
in exactly the same fashion.
It's the same mass, it's the same gravity, it's the same height.
Right. But the power question then came in. Well, how fast were we able to accomplish this? And so what we would determine is that, hey, this was the most powerful situation. This was the second most powerful situation. Depending on your foot speed, either this could be 3 or this could be 3. And then 4 and then 5. So we rated this. And so in the world of exercise, once again, we're back to this whole issue of power. You're more concerned about power than you are work done. And that goes for PE or practice or whatever it is you're going for. So just something to consider. You guys did this really interesting experiment, though, where we didn't have you run stairs. We had you analyze what was going on with an inclined plane. So you started, I believe, with a very shallow angle. And you wanted to get this object from the ground or the 0 level, right,
Right, to some predetermined height.
to some predetermined height. And what you determined is that the distance required to do that was big.
Right,
So you had a large distance, but you had a relatively small force.
right,
So you were able to say, hey, I just calculated some work. And then you were asked to get to the same height.
with much steeper.
Right, so we were steep here. So what happened to my distance?
Decreases.
My distance decreased, but my force had
Increased.
to get bigger, and the amount of work that had to be done was still the same because
Right.
we changed the energy. So the work was equal to the change in GPE, and that was identical in both cases because we were going MGH,
Right, the same height.
the same height. If you put a watch on this, well, then you take this work, and so which is more powerful, and you divide it by the time to hack that out. So a very interesting experiment that the work done is the same, but the power required is different.
Right,
So there's a few other things I want to talk about here. First of all, we know that power can be work over time. And what we haven't covered yet is that power can be force times velocity. So what might be a way to verify to see if this is a true statement? Because we've got force and work, and we've got speed, we've got time. There's a lot of ways with which we could go about this. One would be to try and break this into simpler terms, like,
oh,
well, force times distance is time, and distance over time is speed. That's one way we could do this. You could work the other way from the blue side. Well, you could say force times distance over time. And you could say, well, force times distance is work, therefore, over time. That's one approach.
or we could look at the units.
You could also look at the units. You could say, well, this is a Newton meter per second. A Newton is a kilogram meter per second squared times a meter per second. And simplify. I'm a big fan of this method because it doesn't involve any numbers. So if this is true, then we better get the same thing over here. A work was what, a joule per second? And a joule was a kilogram meter squared per second squared over seconds. And when you get through all this, you do in fact get the same thing. This is called a watt. So power has a unit of watts named after
James Watt.
James Watt. And so just to wrap that up, James Watt, which you probably covered in a history class, was the inventor of I think it's the steam engine. I don't think it's the internal combustion
I
engine.
don't think so either.
And Watt was trying to sell his invention. So he was an entrepreneur, a scientist, an engineer. He was also a businessman. And so when this is, new technology in the late 1700s, early 1800s. And so as with any piece of technology, you have to convince people that it does a job better than the old object.
Right.
So what was the steam engine trying to replace?
Horse and buggy.
Yeah,
Horses.
horse and buggy. He was trying to say that it was more consistent, that it would last longer, that you didn't have to feed it, although that's not entirely true. You have to feed it coal or something. And so this is what he did. He got this horse. And let me be very clear. He got a horse that was dying. And he got it to do a task. Like he got it to walk around in a circle while it was attached to a pole. And he turned this wheel. So maybe it was for a well pump or something. And they did this for 1 hour. And they measured how many times the horse went around the circle in 1 hour. Okay? And then he got a steam engine to do the same thing.
As a comparison.
As a comparison. Okay, so the horse worked for an hour, the steam engine worked for an hour, and of course the winner is
Of course, the steam engine.
the steam engine. Now, even if Watt had picked a better horse, a horse in the prime of its life, the steam engine would have won. Maybe not over the course of an hour, but over the course of 12 hours, 13, 14 hours, the steam engine wins. Okay? But he picked a dying horse because that is now the measurement, the bar with which all engines are measured. Engines are measured in
Horsepower, right?
horsepower. So he picked a weak, nearly dead horse and based all of his steam engine power ratings off of how fast the horse could get the job done. So a little history to go with our physics, and I think that covers it.
Yep.
So work and power and the relationship between the two. Signing off, this is Mr. White.
And Mr. Sadler.